professor here. He's going to go over some of the physics related to our particular challenge in this game this year for robotics. Go for it.
Hello everyone, I'm Mr.Sivel, and I was asked to come in and talk a little bit about the physics behind you're building your robot for this year's competition. I understand it's Recycle Rush, is that correct?
Yes.
Is that right? All right. So we're going to talk a little bit about learning the physics behind the robot. Okay, subtitle, How to Build a Better Robot. When I was preparing for this over the last couple days, I was thinking about exactly why is it that I've been asked to come in and talk a little about the physics. I think of physics as kind of like the rules of the game, not necessarily the game of the Recycle Rush, but the game of the universe. How does this universe work? What are the rules behind it? And in order to build a better robot, you really need to understand the rules of the game and how do they apply. So when I was doing a little research on FRC, I came up with this quote from Simon Helmore, who actually wrote a book called FRC Robotics, the Curriculum. And he says this, I'm a little lengthy here, but let me read this. He says, physics is a model for the world around us, for the world around us. Using this model allows us to predict the behavior and motion of objects, specifically in the case of FRC robotics and their appendages. A strong grasp of physics allows the replacement of guesswork with calculations and will work for the first time. While physics does not determine a design, and in the next few days you're working on that design, so while physics does not necessarily determine the design, it does inform in the process of making that design and provides a ruling for basically what is possible and what is not possible. So there are many, many different topics, many different applications of the physics rules to your robot that you'll be designing over the next few days. But I wanted to pick just a few. Okay, so there, even though you're going to be dealing with, many of you are going to be dealing with the electronics part of your robot in terms of design of the circuitry. I wanted to focus a little bit more on just a few topics. All right. But before we get to what topics I want to focus on, question for you. Okay. Have your meter stick, and what I've done is I've taped a mass, a 200-gram mass to the end, or to one side of the meter stick. What I'm going to do is, some of you have seen this, so don't give it away if you've seen it, but people who've graduated already. What I'm going to do is I'm going to put my two hands at the edge here, and I'm going to actually only move one hand in. So basically I'm going to keep one hand stationary, the other hand I'm going to slowly move in. All right? And the question is, what's going to happen to the meter stick? All right? So again, I'm going to keep this hand still from moving. I'm going to slowly move this hand in. What's going to happen to the meter stick? Okay. Any guesses? What do you think's going to happen? It will what? Stay the same? What do you mean by stay the same? Oh, it won't tip over. Okay, so it'll kind of bounce. Okay, good. Anyone else want to make a prediction? Go ahead.
Yeah, like it'll pretty much like what you said. It'll stay balanced for a longer time.
Okay, it'll stay balanced for a longer time?
Like if you were to move the other hand and then it would tip over really quickly.
Oh, okay, so if I move the other hand in, it would tip over?
Yeah.
Okay.
So you move your hand and until you get past, like I guess where the weight is, that it'll stay balanced. Once you get past that point, it'll like start to tip over.
Okay, so you're saying, well, can I stay balanced, but then after a while it'll tip over?
Yeah.
Okay, all right, here we go. This must be the AP robotics team. All right, so let's try this here. So far, so good. Stay balanced, all right. Now, if I actually move, let me move this one in. Okay, so there was a question of maybe if I move that one in. Let's try that. It stays balanced. Okay. Now, what's happening here? There's a special point here. Does anyone know what that location is called?
Center of balance.
Okay. What is it?
Center of balance.
Center of
balance.
Center of mass, okay, sometimes also known as the center of gravity. There is technically a slight difference between center of gravity and center of mass, but as long as we're here on planet Earth, okay, pretty much the same. I'm going to call it the center of mass today. So there's this special location of where it seems to balance, the center of mass. So that's one of the things I wanted to talk about today. What is the center of mass and how is it applicable to building your robot? I also wanted to talk about torque and how the center of mass and torque kind of deal with the stability of your robot. Because the last thing you want to have happen with your robot is when you lift up one of those, what are we calling these, crates? Totes. Okay, so when you lift up one of the totes, or you go over that little 2-inch incline, you don't want your robot tipping over, right? And so I wanted to kind of talk about how can you build a better, stable robot, okay? All right, so first let's talk about the center of mass, a little bit of what that is. First of all, the definition, it's the location where all the mass of the system is located or can be considered to be. So in other words, with this object, even though some of the mass is over here, some of the mass is over here, you can treat all of that mass as basically at one location right about here, okay, where I balanced it. So we can treat your robot, and again, this is somewhat of an oversimplification, but kind of doing kind of a first order here. All the mass at a specific location called the center of mass, okay? It's this center of mass in combination with what forces are acting on your robot and where those forces are located, they're going to determine whether or not your robot is stable or not, okay? So since we basically want to make sure that our robot is stable and does not tip over, we need to be aware of where the center of mass is, whether it's high in the robot, low in the robot, what forces are acting on that robot, where those forces are kind of being applied, and thus whether your robot will stay upright, okay? So if we start back with just a simple meter stick, this time with no mass, approximately where is the center mass of a typical meter stick? Right at 50 centimeters, right? Right in the very center. And so I have this, we should be able to balance that approximately right at 50 centimeters. Okay, so that thing's going to stay balanced more or less. But what happens if I put a mass on one end? Okay, so let me do that. And so if I put a mass on the end, it no longer stays balanced, right? I have to put another mass on the other side. Now, unfortunately, I don't have a mass that's exactly the same as the one over here. This actually is, I think, a 200 gram. This is a 500 gram. So where must I put this 500 gram for this balance to balance?
Closer.
Okay. So what I'm hearing is basically location does matter. Okay. In fact, it's not going to be the same distance away. In fact, you notice if it's farther away, it doesn't seem balanced that way, but if it's too close, it's not balanced that way. There's some place where it's just right. It's that kind of that Goldilocks syndrome. Not too far, not too close, just right. And if I get it, it will be somewhere around there. Without wasting too much time. There we go. Okay. All right. So this leads us into the kind of a next topic, which is torque. But before I do that here, I'm going to talk. Let's see here. How many of you? Everyone needs a pencil and a paper clip. So I tell you what. Could you guys help me out here? Make sure everyone gets a paper clip, and make sure everyone gets a pencil. So everyone needs a pencil with a rubber, with a eraser on top, and a paper clip.
Is that almost 50%?
I got it's the same as finding the midpoint on your
Alright, while we're passing around the paper clips and pencils, perhaps some of you have seen this kind of little toy. It's kind of a little bird here. And what's neat about this bird is I can take it, put it on the table's edge, and it will actually kind of just stay right there. Okay. Now, the reason for it is because of where the center of mass is. It turns out that this bird has a lot of weight at the ends of the wings. Okay? And because of that, where is the center of mass of this bird? Okay, it's going to be, in terms of this way, more up here than down here because the masses are up here. All right, and somewhere kind of in between. In fact, the center of mass actually is somewhere, actually it's probably just right under where the beak is. And so I can actually just put this right on the ledge of a table, and it looks like it's kind of floating there. Okay, so what we're going to do is, could we do the same thing, say, with a pencil and a paper clip? Could we do something where we could kind of basically have the pencil kind of hang on the side of a table ledge? Okay, what could we do? So what Okay, well, the answer is, well, actually, before I show you kind of what it looks like, all right, go ahead and take a moment and see if you can do it. So take your paperclip. Feel free to manipulate your paperclip for a second, okay, and see if you can get that pencil to kind of stay off, basically stay off the ledge.
Turn away. Turn away.
Yeah. Feel free to open up the paperclip if you want to. Some of you are getting.
I didn't have much space.
Release, Josh.
As long as it's balanced, as long as it stays. All right. All right. You're not quite sure how to do this. If you take your paperclip and kind of open it up and make it like this, stick it in the eraser. All right. You can actually then take that and suspend it from the corner of a table, and it will stay there. Okay. It'll stay there all day long. Okay. Now, is it physics or is it magic? All right. It's physics. All right. The reason for that is, where is the center of mass? Okay. Well, most of the mass is the pencil, right? And it's going to be somewhere along the pencil. It's actually a little bit higher towards the eraser. All right. But with that paperclip, it's also kind of projected out a little bit. Turns out that you can actually tell exactly where the center mass is, because once you get it balanced, the center mass is going to be directly below that fulcrum point, that point of where the paperclip is connected to the table. Okay. All right. So there we have the center of mass. Okay. And we can treat all the forces acting on that pencil as if it's behaving at that one location. All right. Now, have your foam pad with a pen in it. Okay. All right, Daniel. What I want you to do is I want you to see if you can somehow get that system, that pen/foam system, to balance, so it doesn't topple over. Okay, right on the table. Okay, see if you can get it to balance so it does not topple over. You know, this is the AP robotics. That's exactly right, actually. Okay, notice here. That's exactly right. All right. Notice it's very stable. It's not gonna fall over. All right. Now, what most people I would have thought would have tried first was something like this. All right. Problem is, what happens? Okay, it falls over. Right. Exactly. All right. Now, what's the difference? Okay, what's the difference about trying to do it this way versus trying to do it that way?
Surface area larger than the tip of the pen, so it has. Well, because it's a bigger thing, it has a more centered kind of
Okay, think about what we just talked about. Okay, what were we just talking about with this? What's the physics concept? Center of mass. Okay, think about center of mass in terms of the styrofoam with pen. Where's the center of mass? Yeah, somewhere in the styrofoam. I mean, probably somewhere towards the center of the styrofoam, somewhere down in, probably literally in the styrofoam itself. Okay, so if I tried this, where's the center of mass? Probably way up high, right? Where's the center of mass? Much lower. So does it matter where the center of mass is in terms of stability? Yes. Ah, yes. Okay. Turns out a lower center of mass is going to give you a better stability. Okay, we'll talk a little bit later in a second why that's the case. All right, but there really is no difference in terms of this and that in terms of the object. It's just where we put that center of mass. Okay, here it's a high center mass. All right, center mass kind of is actually trying to go down. Here the center mass is low. If I were to try to tilt that, I would actually have to increase the location of where the center mass is located. Okay. All right, so not only is it important where the center of mass is, but it's also important of what forces are acting on that object. Okay, and that leads us into the concept of torque. Okay. Torque is basically, and there's kind of different definitions, but essentially it's the product of two vectors, as we call it. Okay, it's the measure of force's tendency to produce a rotation about an axis. So why is it when I have this styrofoam, why does it want to kind of tilt over when I do this? Why does it tilt over? Because there's some force that's trying to cause it to rotate. Okay, and what force that, or where that force is located, is going to determine how much torque there is, and the torque is going to determine how much. Basically, how much it's going to rotate. Technically, it's change rotation, but we'll just say it's the motion. Okay. So, what is important about where is the force located? Okay. Not only the strength of the force, but how far away that force is from what's called the fulcrum, or that pivot point. All right, and so for instance, out here, okay, when I put this mass in originally, okay, this object wanted to rotate that way. Okay, there was a net torque this way. Okay, so to basically balance, I need to put a force over here that's going to basically cause a torque in the opposite direction to cancel it out. Okay. Now, which of these two masses is heavier?
One on the right.
Yeah, obviously this one over here is heavier. It's going to exert a greater force down than this guy. And so for the torque to be the same, and if our definition is basically that torque arm, which is the distance from the fulcrum out to where the weight is located, if torque is by definition that distance times the weight, in this case, which is the force, then where must I put this object? Okay, should it have a smaller lever arm, okay, or what we're calling your torque arm, but a shorter lever arm, or a larger lever arm compared to this guy?
Shorter.
Okay, yeah, greater force, shorter, and so that's why when we do get this balanced, somewhere around here, there we go. You can see that essentially for a less force, longer distance away. Okay? If you have an object, for instance, if you're pulling up a tote that weighed more, then if you had the same distance away as one that weighed less, there would be more torque on your robot trying to topple it over. Okay? All right. Any questions so far?
So you can do math on that and figure out where those things are.
Absolutely, absolutely, yeah. I tried to stay away from the math here a little bit, but, oh yes.
Since we know the weights, we know the forces, we can calculate the force arms.
Exactly, yeah, all right. What we're gonna do next is kind of one of my kind of favorite activities. If any of you, let's see, did any of you go to the Physics Olympics last year? Those who, was this one of the activities they did? Balancing on a, okay, we're actually gonna try this. What we're gonna do is we're gonna see basically, we're gonna have a plank of wood, and we're going to see how far out can we put a person. Okay, the farther out on the plank, the higher our score, so to speak. So let's see here. I need 3 volunteers. All right. How about 1, 2, 3? You guys know where the first hands up. Come on over here. Okay. So what we're going to do is let's see. Who wants to walk the plank? All right, well, your name?
The pirate.
Nick the pirate. Okay, Nick. All right, Nick, what we're going to have you do is the goal is for us to get you as far out on the plank as possible. Okay. Your 2 partners, okay, who are Isaiah and Matt. All right, Isaiah and Matt are going to basically be also on the plank, okay, but helping you get as far out. Okay. So, gentlemen, there it is. Okay, go ahead and put it up on the platform there, and let's see how far we can get. Matt, was it? Nick, I'm sorry, Nick. Okay, so let's see how far we can get Nick out. Okay. Whoa. Yeah, after a while you can go down.
Touching the ground.
Don't be on the table if you can. All your force.
Okay, don't use the table. That's cheap. Okay. All right.
So about like.
All right. So Nick, it's about there. Okay. So how far? You're probably about a meter out. Okay, not too bad. But is there any way we could get you farther out?
If I lean that way.
If you lean that way, okay.
But then I'm gonna fall.
See, I'm worried.
What else
What else could you do?
What else
think
can you
about.
do?
Oh, okay. Isaiah has an idea.
Moving the plank that way, yeah.
All right. Yeah. You guys can help these spotters here. We don't want to make sure we don't lose anybody on the robotics. Okay, so it looks like Nick is now farther out than a meter before than it was before.
I hear the wood snapping.
Not good. All right.
All right.
All right.
One more.
Last try. Just another minute or so.
All right, get up here.
Right.
Get up. All the way at the end. Yep.
Are we gonna be able to get Nick all the way out to the end?
And here's the wood snapping.
Wood snapping.
Yeah.
Don't hold it like this. Wood snapping.
There you go.
All right. We got Nick all the way out to the end. All right.
I can figure that out here. I get off.
All right. All right, yeah, we don't want to seesaw here today. Okay, nice job, guys.
I need a hazard.
So notice where they positioned themselves, where Isaiah and Max put themselves, they were able to get Nick farther out. Originally it was only about 1 meter out, and then he got him eventually out to the total end of the plank, which was probably about 2.5 meters or so. All right. All right, which leads us now to the question of stability. And this is ultimately where we want to go to. We want our robot to be very stable. We don't want it to tip over, as we said, when lifting something up or going over those little inclines that you have. All right. One of the ways you can keep it stable is by knowing where the center of mass of your robot is and keeping it as low as possible. All right. So, for instance, here we have 2 cars. Okay. Let's say these 2 cars have the same mass, but one is kind of a skinnier car than the other. All right, which one would have a lower center of mass?
The skinnier.
Okay, the wider one or the skinnier one?
Neither one.
Skinnier.
No, wider. It says stable and unstable.
Yeah.
Skinnier.
All right. Yeah, I think I kind of put myself in a corner when I said they had the same masses. Anyways, generally speaking, though, a wider base is going to help you with a lower center of mass. Okay, and I'll show that to you in a second why. But let's see here. Yes. Okay. Now, if we tilt an object, okay, one way to keep it from toppling over is if we draw a vertical line that goes through the center of mass. So here's the center of mass. If we draw a vertical line, if that vertical line stays between the base, okay, so in this case for a car, say between the 2 wheels. On your robot, it'd be, well, probably also between, most likely the 2 wheels as well. But if you keep that vertical line that goes through the center of mass between the base, then it's going to be stable. It will not tip over. But as soon as that line is on the outside of the base, it will tip over. Okay. So let's see. I need a volunteer here. Okay. How about someone? It's the same volunteers. How about? All right. Connor. Okay. Okay. Connor, what we're gonna have you do is let's see here. Where to do this? All right. Now I want you to just go right over there to the door. All right, now Connor, let me face this. Where do you think Connor's center of mass is located? Okay. For men, it's somewhere probably around here. Okay, near the belly button. Okay. For women, all right, it tends to be a little bit lower. Okay. Without getting. All right, wait, just okay. As far as I'm going, all right. But there is a little bit difference between genders, all right. But anyways, for Connor, let's say it's your belly button, okay. So what we're gonna have you do is turn your side so you have one side against the door, and put your right foot up against the door, okay. And if you want, you can put your hand up on the wall as well. Oh, that's fine, okay. Now, what I want you to do is, while staying balanced, I want you to kick your left foot out, like that.
So,
all right. Wait, just like this. Just put your foot out like that, bounce.
Okay.
Like, foot against the door there. All right.
And I have to push against the
Well, no, actually, not specifically. Well, I mean, you can actually just keep your hand to your side. I'm just saying. Okay. All right. You notice how it's basically impossible. Okay. Now, why is it that I can do it here? Okay. But Connor can't do it over there against the door. Yep.
Because you also have a force acting on the other side because there's opposite reactions.
Okay, so you're kind of almost thinking in terms of like Newton's third law. For every action, there's an equal opposite reaction forces. We could probably think about it that way, but I want you to keep in mind what we've just been talking about. Yep.
You're leaning over your other leg, and Connor can't do that because he's up against the wall.
Ah, yeah. If you notice, when I do it, there's something I kind of do. Okay, watch my body. Okay, where's my center of mass? Pretty much straight down the middle, right? Okay, so it's kind of like between my feet. Okay, so if I take one foot out, okay, what do I have to do to keep myself balanced? I need to keep that center of mass over what part of my body? Over the other foot. Okay, so I can basically move over a little bit. Okay, Connor, on the other hand, is against the door. He can't do that. Okay, so he's unable to do that. Okay, Connor, thank you very much. Okay. All right. the AP class, so I better just use a $1 bill for this one. Keep my 20 in there. Okay, who wants the chance to earn $1? Now I get lots of volunteers. I should have started with this. Okay, what's your name? VJ? VJ, all right, VJ, would you like to earn $1?
Yes.
So would I, okay. I guess you want, okay. So VJ, come on up here. Okay, I'm gonna put that $1 down, okay? And what you wanna do is stand about a foot away from that $1, okay, just like that. In fact, why don't you come over this way, because that way they'll get the prettier side of you, and not the back side, okay? Now, what I want you to do is, without bending your knees, okay? Just bend over and pick it up. That's all you gotta do. All right. All right, now you didn't win the $1 yet, okay? What I'd like you to do is we're gonna go back to that door. All right, and we're gonna do the same thing, but this time you're gonna be up against the door. Okay, we're gonna put that down there. If you can, without bending your knees, all right, BJ, if you can, without, yeah, you got your feet up against the back, right, up against the door. Without bending your knees, if you can pick that $1 up, it is yours. Okay, you gotta bend straight up. You can't. Come on, we all want to see you fall. So go ahead.
Go onto your toes, VJ.
What?
Go onto your toes.
Yeah, go on your toes. That's what I'm trying here, but I gotta bend my knees to do that.
VJ, do you want me to bend you just?
All
right. All right.
You almost had it. Come on.
Almost. All right. Let's give VJ a hand. All right.
$1 for you.
Yeah, it's the same thing. When you go to pick up, without bending your knees, what do you have to do? You have to keep your center mass over your feet. And so when you're bending over, you have to have some part of your body go back, all right, to basically keep that center mass over your feet. And so what do? Push out your derriere. Okay? Now, I mentioned there's a difference between men and women. Women tend to have a lower center mass. There are some people, some women, some guys too, I suppose, but some people are actually able to do this, okay? Is there any woman who would like to try this? All right. Good thing I already ate lunch. I don't need this $1. You might get it. All right. Yeah, just right up, just put your feet up right against it, and we're gonna put that there, and we're gonna see if you can pick it up. It is yours. Look at that. Good job. All right, you? Say you. Say you. All right, let's give her a round. Okay, just a couple more minutes here. I don't want to take too much of time because I know you guys have a lot of planning to do. But I want to get back to this idea of stability, okay? All of you have done this before. You're sitting in your chair, you're bored a little bit, and so you kind of maybe start to rock on your chair, okay? Now, without going too far, what I'm going to do is just rock back on your chair a little bit, no more than an inch. Okay? All right. Now, when you did that, okay, yeah, don't leave. Yeah, it's, all right. Don't get me in trouble here, all right? All right. Where did your center of mass go when you leaned back just a little bit? Did it go up or down, or did it stay the same height? Okay. It actually went up a little bit. Okay. Your center of mass actually went up a little bit. Now, turns out, and there's a couple of laws of physics that generally can be summarized as this, okay? Nature is lazy, all right? And objects want to naturally go to the lowest potential energy, okay? That's a summation, that's not a technical law, but it's essentially what some laws of physics kind of generally say. And so when you lean back a little bit, your center mass goes up higher. That's a higher potential energy of your body. And it's gonna naturally want to go back down, okay? And so that's why when you let go, all right, it goes back down. Now, when you lift it up, your center of mass was still within the base of the chair, and so it rocked back to where, kind of back forward. But if you did this, and don't do this, but if you did, rocked up high enough, all right, to where essentially you get to a point of where the center of mass is as high as it's going to be, and the center of mass, if you tilt a little bit more, goes back down, you're basically going to fall backwards. So if you've ever been on a chair and you rock back too far, then what happens is you got your center mass too high, and the center mass is going to naturally come back down, and you fall backwards. Okay. Yeah. So this essentially leads us to so for instance here, this object is what we call in stable equilibrium, because if we were to tilt this, all right, the center of mass would have to go up a little bit higher, okay? And so the center of mass goes up a little bit higher, it's going to come back down and be stable. But if, for instance, here, the center of mass is at a point where any tilt is going to cause the center of mass to go lower, it's going to tilt over, okay? That's the difference between what's called a stable and unstable equilibrium, okay? But ultimately, this leads us to the question of a robot, okay? Let's see, do I have a place to write? I guess, can I pull this up and write this? Okay. see, is there a
Oh,
cover?
we just cover it with something. I usually just throw a piece of paper over it. Yeah.
Is this fine? Okay. Yeah, do you have any others?
We're on the rail, there's a whole collection.
Okay, so kind of to wrap things up, let's say we have our robot. Okay, all right. I was not an artist, so there's your robot. Okay, where's the center of mass of your robot? Okay. All right. Let's assume that you built it and it was fairly kind of low. Okay. Let's say probably you have more parts down below. Okay, so let's say the center of mass is there. And here we have kind of a box or a tote that we want to lift. All right, the center of mass of the tote is going to be right there. Now, if we treat, once your robot picks that up, all right, you can treat the whole thing as one system. Where is the center of mass of that system? Okay. It's no longer here, but it's going to be a little bit closer to here. In fact, if you draw a straight line between the two center masses, all right, and do a little bit of math, all right, you can actually determine the center mass is probably somewhere right about there. Okay, so X marks the spot. All right. Now, let's say the robot lifts this up a little bit higher, let's say about halfway up. Okay. So there's the center of mass of the tote itself, but where's the center of mass of our robot with tote while it's holding it there? Okay. Well, if we draw a straight line from one center mass to the other center mass, it's going to be along that line, and maybe it'd be right about here. Okay. X marks the spot. And finally, if we lift that tote up even higher, all the way up to the top, because we want to get those, was it 20 points, I think, if we put it on top of another tote? All right, so here's the center mass of the tote. We draw a straight line from there to there. Okay. Where is the center mass? Maybe some point, say, here. Okay. Now, notice what has happened. Yeah, okay.
So would you say the center of mass is the midpoint of the line?
Not necessarily. It would only be the midpoint if essentially kind of like the masses of your robot and tote are kind of the same. I presume that these totes are going to be probably much less massive than your robot, so the center mass will be much closer to the center mass of the robot. But it will migrate a little bit as you lift this up. You notice how the center mass has shifted, and this is kind of greatly exaggerated. Okay, but the point I'm trying to bring is notice how the center mass has shifted. Okay, the center mass has moved upwards vertically. Right. So now, remember how we talked about with a low, for stability, you want a low center mass, but when lifting the tote up, the center mass is now higher. But also look what has happened to it. Not only has it gone higher, it has moved horizontally. Okay, see how the center mass has moved, has shifted over this way? Okay, and when do we have stability? Okay, when the center of mass is located where?
Between
okay. And when a vertical line through the center mass is basically between the base. So here, the center mass is between the base. This is the base of your robot. Okay, and so it's stable. Okay, here, the center of mass is like right on the edge. And so this robot is starting to get a little tipsy. Notice up here, when the tote is up here, your center mass is actually outside of the base. And so what would happen? In this case, the robot would tip over. Okay? To make things worse, let's say you have your robot trying to carry a tote on an incline. You're trying to go over the hill. All right? That can make things even worse. Or maybe in this case, instead of having your tote that way, you put it down this way. Okay. Notice where is the center of mass in this case. Even if the center of mass was still like inside the robot, all right. If I draw a vertical line, notice how that vertical line is outside the base. This guy is going to tip over. Okay. So when designing the robot, think about the concepts of center of mass and torque and stability, and then also when running your robot, all right. Think about where if you have that tote up really high, that's going to affect where the center of mass is. It might affect kind of the ability to go over a ramp, such. So, yes?
And we can use math again, right?
Oh, definitely.
We know the relative weights of the tote and the robot, and then I think it's a ratio, isn't it, between the two centers?
Yeah, essentially, if you can treat this as like a two-particle system, the center of mass, this would be like the location or position of the center of mass, is equal to the position of object 1 times the mass of object 1 plus the position of object 2 times the mass of object 2 divided by the sum of the masses. Okay, so that's actually kind of how you can calculate where the center mass is for a two-particle system.
I think we're gonna have to do that, guys. We talk about a stack of maybe 4 totes, however many.
Yeah.
You know, we've got 28 pounds to balance against our robot, which is maybe 120, and we're gonna have to see how does that work. All right?
All right. Well, thank you for your time and your attention. I appreciate it. Any other questions before I go?